So what we're going to talk about next is boiling point elevation. So this is our first colligative property we're going to discuss. I'm going to show the formula. The math isn't too bad once you understand the pieces, so I'll leave that for the practice worksheet. But I'll kind of walk you through what all of it means, what's going on. And so as you dissolve more and more solutes into your solution, as it becomes more and more concentrated, our molality increases. What's going to happen is your boiling point is going to become higher and higher. So the boiling point is going to move up, because what it means is that we are able to remain at a non-boiling liquid at higher and higher temperatures. Because what's going on is the solutes are holding back the solvent particles from escaping from the liquid phase to the gas phase. They're being held back by the solutes. And so it takes more energy to bump them out into the gas phase. And so that means that our boiling point moves up. So end result is liquid phase is more favorable. Okay, so that means the boiling point moves up. And so the change in our boiling point, this is going to be a positive value, is equal to I Kb times m. And so I is the Van Hoff factor, and there's the theoretical kind of approximation of it, and there's the physical reality. And so the theoretical approximation is just the number of dissolved particles per molecule. So ionic compounds are going to break into their constituent ions. Covalent molecules are going to dissolve whole, they're not going to fall apart. And so for a covalent molecule, it's a 1. 1 mole of sugar, it's all covalently bonded, I dissolve that in water. I have 1 mole of sugar molecules floating around. So it's 1 to 1. If I dissolve something like sodium chloride, it's going to fall apart. I'm going to get Na pluses floating around, and I'm going to get Cl minuses floating around. So if I dissolve a mole of this stuff, I get a mole of Na pluses and a mole of Cl minuses, so it essentially doubles. It's a Van Hoff factor of, I've got 1 particle, 2 particles, so I equals 2. It's a Van Hoff factor of 2. So ionic compounds are going to have Van Hoff factors that aren't 1. Now the physical reality is it's actually like a 1.8 due to like some sort of weird solvent effects and things like that. But you don't have to worry about that now. If you see it come up anywhere, just be aware that it can actually be decimals, because there are kind of some mitigating factors. But the theoretical number is 2, because you get 1 cation, 1 anion. They're not floating around stuck together, they are floating around separately. They are different particles floating around. All right, and then the next thing is Kb, and that is just a constant. And as always, we've gotten very creative with the name. It is the boiling point elevation constant. Why do we call it the boiling point elevation constant? You're definitely asking yourself. Well, that is because it is the constant in this equation to find the change in the boiling point. So we don't leave a lot of mystery there. And how do you know what that is? Well, you're either told in the problem or a table is going to tell you. So it just depends on what the solvent is. Water is going to have a value for Kb. Rubbing alcohol is going to value for Kb. Olive oil will have a Kb value, so on and so forth. And the last thing is, there it is, the molality of solution. So we're going to talk about concentration in terms of molality. So this equation relies on the unit of molality. That's why I introduced it in the last video. And so, if you know the molality of your solution, you know your Kb, and you know your Van Hoff factor, which again, if you know what you're dissolving, you can figure out your Van Hoff factor. If you know what you're dissolving it in, you look up Kb, and if you know how much you're dissolving and into how much solvent, you calculate M. You multiply them all together, you get the change in your boiling point. Now that's not your new boiling point. That's like, you run a marathon and then you go sit on the couch, and then you move to the other side of the couch and someone's like, you only moved like 3 feet today. Well, you did too many miles running first, but that was a small change, but there was the initial amount, right? And so, if you calculate all this and you get like a 4 here, it doesn't mean the boiling point is 4 degrees Celsius. It means it is 4 degrees Celsius higher than it was before. And so if this was like a water solution, it'd be 104. And so just remember that the boiling point of the solution, we've got to take the original and we got to add the change to it. Okay, so if it was water, original would be 100.0 degrees Celsius. We add 4 degrees to that, we get 104 degrees Celsius. So just keep that in mind. This is not the new boiling point, it's how far we have moved to get to the new boiling point.